So stereochemistry overall is focused on the 3D orientation of a molecule in space. Okay, so in our workshop for stereochemistry labs, we will be building these molecules and we'll be looking at how they exist in space. And your stereochemistry largely focuses on a tetrahedral carbon. So that is a carbon, a single carbon, with 4 single bonds coming out of it. Okay, so we're going to focus on that tetrahedral structure. So if you don't know what tetrahedral means, if you don't know what that geometry is, please go and revise your notes. When we're examining this tetrahedral carbon, we're going to be looking for specific traits, and we'll talk about that now as we progress through the lecture. One of those traits is chirality. Okay, and the word chiral is coming from the Greek word meaning hand. So if you held out your 2 hands in front of you, they are mirror images of each other. Okay, so your left hand and your right hand, and we lay them flat side by side and look at them, they are mirror images of each other. However, keeping them as they are, if you bring your right hand on top of your left hand without switching or moving anything, you'll see they're not superimposable. Your thumbs dangle off on either side, okay? So they are mirror images, but they are non-superimposable, and that becomes very, very important, okay? So essentially your hands are lacking a plane of symmetry, they're asymmetrical. Okay, so we can also have molecules that are mirror images, so if we lay them down side by side, they will be mirror images of each other, but if we try to overlap one on top of the other, due to their configuration within a 3D space, they are not superimposable. Okay, and usually when you have those 2 things, so being mirror images but not being superimposable, they will be lacking symmetry. So this is an important definition. So what we've already said, when we have a chiral molecule, it is a molecule that is a mirror image. Okay, it's a mirror image and it's non-superimposable. And the most useful piece of this for us is going to be it must have 4 different groups attached. So we're going to explore that a little bit more in a moment, based solely on a single carbon in a tetrahedral structure with 4 bonds, 4 single bonds coming out of it. Okay, so for a moment, let's look at that in greater detail. So when we're determining chirality, you have to say if a molecule is chiral or if it is not chiral, and the word we use for not chiral is achiral. Okay, so if it is chiral, it is going to have 4 different groups attached. So very, very quickly here we can see that we have a carbon and it's just bound to this generic, we've just made up an atom or a molecule, it's called A. We have 4 bonds from this carbon and all 4 attached to the same atom, okay, the same A, it is achiral. Same here, okay, we have 3 and we have this random B, it is still achiral. And same here, and eventually we come to a molecule that we can work with. We have an A, a B, an X and a Y. We have 4 entirely different groups attached, and therefore it is chiral. Okay, so you're looking for 4 different groups attached to this carbon. What we are also looking for, because sometimes we are not only looking at single carbons, we are looking at single carbons within a larger molecule, and a quick scan for us to be able to do is to look for symmetry within that molecule, because as soon as we find symmetry we say it cannot be chiral, therefore it is achiral. Okay, it is not chiral. So when we have a molecule like this, okay, if we just draw an invisible line down the centre, if we can fold the left side and the right side over together like a book and everything lines up properly and perfectly, it is achiral because it is symmetrical. And sometimes that's more obvious to us, okay? So in these examples here, okay, particularly in this middle and this one here, we can fold them over perfectly and we know they're going to align perfectly. That OH is going to overlap on that OH, that hydrogen is going to overlap on that hydrogen perfectly. And it is symmetrical and it is achiral. Okay, so there's no carbon within that structure that has 4 entirely different groups. And the same here, we can fold the left side over to the right side, making them perfectly symmetrical, mirror images, therefore they are achiral. It's easy sometimes when we look at it kind of flat like this, when we're looking at it as a 3D structure, it can be a little bit more difficult, but this is essentially what you're imagining. So you can take your kind of flattened structure that we'd usually draw, you can put it in a 3D space, and again drawing that imaginary line right down the centre of the molecule, and we can see that this is still a chiral. It's non-chiral because these two CH3 groups are still going to they still provide a plane of symmetry, so therefore it's not chiral. So remember, as soon as you have two or more identical groups, it is no longer chiral. So maybe let's have a look at a molecule that is actually chiral. Let us see what we're working with. So we have 2-chlorobutane, and we have no plane of symmetry when we draw 2-chlorobutane. So maybe let's draw it out ourselves so we know what we're looking at, because we're new to this, aren't we? So we're not fully sure just yet. So 2-chlorobutane, I'm going to remember that word. So I am going to come over here to my whiteboard, and I'm going to draw out 2-chlorobutane as we normally would. So I have 2-chlorobutane. I have said that a lot so far. 2-chlorobutane. But tells me I have 4 carbons in a line. Ane tells me I have single bonds between all of them. 2-chloro. So number it whatever way you like. I'm going to go this way. So I'm going to have a chlorine on position number 2, and everything else is going to be a hydrogen. Now, looking at this molecule, we can go through carbon by carbon just while we're getting used to things and saying, is any or are any of these carbons chiral? And this is what we usually do when we're first starting with something. We take it step by step, okay? Don't jump to the end. So carbon number 1, let's have a look. It is bound to a hydrogen, a hydrogen, a hydrogen, and this big group. And I suppose this is something to point out. You have a hydrogen, a hydrogen, a hydrogen, and this is what it's bound to, this whole thing. Okay, so just keep that in mind. So it has 3 hydrogens, and it has this CHL, CH2, CH3 group. Okay, so that's just considered one substituent group, and that can sometimes throw students off, so just be wary of that. But because it has those 3 hydrogens, that cannot be chiral, okay? Because we need 4 entirely different groups. So I'm just going to undo my notes there. So we know this one is not chiral. Let's look at carbon number 2. That carbon is bound to, we have a chlorine. I'll try to use some different colours so it's a bit obvious. It's bound to a hydrogen. It's bound to this group here, which we know is a CH3 group, and we know it exists as a group. We know it can be clumped together. And then the last thing it's bound to is this big one here. Okay, so it is bound to 4 different groups. If I drew it out, I'd say that's a carbon, so this is my blue carbon in the middle. It's a chlorine, it's a CH3 group, it's a hydrogen, and it's a CH2, CH3. And now I can very clearly see that that is bound to 4 different groups. So this is chiral. Okay, so this carbon is chiral. And that's what we want to see, okay, that's good. So you can do that throughout the rest of the molecule, because sometimes molecules have more than one chiral carbon. So it is good practice to make sure you kind of quickly scan all your carbons and see, are they chiral or are they not? So again, if I have a look at my structure, and just quickly draw it out. So I'm drawing the exact same structure. And we said we have a Cl here. We already said that this one is not chiral because it had 3 of the same groups, 3 hydrogens attached, so it cannot be chiral. We said this one is chiral because it had that CH3, that chlorine, the hydrogen, and that CH2, CH3 group, so that is chiral. This one here, and you don't have to go and draw them out every single time, you can very quickly see that this carbon here has 1 hydrogen, 2 hydrogen. As soon as it has two or more of the same groups, it is no longer chiral. It cannot be chiral. So we forget about it. Okay, so that is not chiral. And the same here on this very last carbon, carbon number 4, it has 1 hydrogen, 2 hydrogen, 3 hydrogen. It cannot be chiral. So it gets a big X from us. So we only have one chiral carbon within that structure. So the structure itself is chiral, but you have one chiral carbon, okay? So the molecule can be described as chiral, okay? And you can say there is one chiral carbon. So the molecule can be chiral, but the carbon is a chiral carbon. And that chiral carbon can also be known as a stereogenic center. Okay, so you can call it, maybe we'll type it here. So you can have a chiral, this is working for me, chiral carbon, which is the same thing as a stereogenic center. And having one or more of these will make the overall molecule chiral. Okay, so just keep that in mind. We can have one or more of those. Okay, so let's go back to our notes for a second. So that was just this one, okay? And usually if you're asked to draw a molecule like this and you find a chiral carbon, you just indicate it with an asterisk. So an asterisk is just that little star. So for example here, you could just draw a little star here, and then you'd be indicating that that carbon is chiral. Okay, so an asterisk is that weird little star. So we can look at another example, okay? So our example here is 2-bromobutane. So it is a chiral carbon. You're being told here it is chiral. Okay, or sorry, it's a chiral molecule. So it has a chiral carbon, or again, a stereogenic center. And that particular carbon is bound to 4 different groups, and therefore we have no plane of symmetry. When you're dealing with chiral carbons, okay, or chiral molecules, you always draw both mirror images. So let's have a look at that. So again, we're drawing 2-bromobutane. I'm going to just come up here. So I can draw 2-bromobutane the way I'd normally draw any molecule first. So butane, tell me I have 4 carbons in a row. 2-bromobutane, tell me I have a bromine here. Everything else is a hydrogen. So we should be very comfortable at this part. Now, I can quickly go through my carbons and say what is chiral and what is not, based on it having 4 different groups attached. So, I'm going to number these. 1, 2, 3, 4. So I have 4 carbons. I'm hoping I have at least one that is chiral. And remember, as soon as we have 3 of the same group, 2 of the same group, it's gone. It's not chiral. So this carbon number 1, we have 1 hydrogen, 2 hydrogen, 3 hydrogen. It cannot be chiral. I'm going to just jump around because I feel like it. The carbon number 4, we have 1 carbon, 1 hydrogen, 2 hydrogen, 3 hydrogen. 3 of the same group, definitely can't be chiral. We have carbon number 3, we have 1 hydrogen, 2 hydrogen. If I have 2 of the same groups, I definitely don't have 4 different groups, so that is gone. Leaving us somehow with only carbon number 2 to deal with. And let's just have a look at carbon number 2. Carbon number 2, we have a bromine group. We have a hydrogen. We have a CH3 group. And finally, we have this CH2, CH3 group. So, this is chiral. When you have your chiral carbon, when you've identified your chiral carbon, you're now going to just draw that tetrahedral structure, focusing solely on that carbon. And we're going to do this, and we're going to have a template, okay? So when we're drawing a tetrahedral structure, you have your carbon in the middle. In a tetrahedral geometry, you have 2 bonds that are flat against a page. You have 1 coming out towards you, that's the solid wedge that we've definitely encountered before. And you have 1 going back in space. Okay, so this is your molecule. Right now, because of the structure, the way it's been given to you, you can put these bonds anywhere. It doesn't matter which one you put at the moment. If you're given more details, for example, if in the structure you already had this dashed wedge and this solid wedge, you might have to be a bit more careful. But for now, let's not worry about that. So now I'm going to say, well, I have my CH3 group, because now I'm going to summarize those groups, aren't I? I don't have to go and draw out the CH2, CH3 as it is. I can summarize it, I can condense it. I have a hydrogen, I have my bromine, and I have my CH2, CH3 group. Okay? So I've taken my chiral carbon, maybe I've labelled it with a little asterisk to say this one here is chiral. I've now drawn my tetrahedral structure to show that chiral carbon, to focus in on that. And because it is chiral, I know it can exist as itself and as its mirror image. So I'm now going to draw its mirror image. So that's what you'll always do. Okay? You'll go from the structure provided or the name, you'll identify the chiral carbon, you'll draw the structure based on that tetrahedral structure of that single chiral carbon, and you'll draw its mirror image. And what do I mean by its mirror image? You're going to pretend that this line down here is the mirror, and you're going to flip the molecule. So when we're flipping the molecule, you're still going to have your carbon in the middle, and then, as with a normal mirror, whatever is closest to the mirror on one side is closest on the other, and whatever is furthest from the mirror is going to be furthest on the other side. Okay, so if you brought your hand up to the mirror, you'd see the reflection of the hand is right up close to it. If you extended your arm away from it, you'd see the mirror image that it's also far away from it. So bromine stays the same, that doesn't need to change. Okay, it's just going up, so the distance from the mirror isn't changing. What is changing though, this one, okay? So it's close on this side, so we need to bring it close on the other. It still also has that dash bond, so you're not changing any of those bonds at the moment, okay? Draw the mirror image of exactly what you see. So CH2, CH3. Okay, so I'm just drawing the molecule backwards. That 3 really should be here. Okay, what's furthest away from my mirror is that CH3 group. CH3. And then this one is coming a little bit out, a little bit away. So you can see how it is a mirror image. Okay, so when I have that, we have what is known as enantiomers. Okay, so this is a type of stereoisomer. So they are non-superimposable mirror images of one another. So that means if I try to pick one up and lay it on top of the other one, I couldn't, okay, because their spatial arrangement would not allow for me to do that. I know it looks like we could maybe here, okay, because it's flat, but when we actually go to build these structures in the lab and try and physically pick one up and stick it on top, you will find that they cannot align. Okay, but this is what you'd be doing, okay, this is how you'd be drawing things out. Let's just flick back to our notes. And this is just what we have here, okay, so we've taken our 2-bromobutane, we've identified our chiral carbon, and then we've drawn the mirror image of both of them, okay, so the chiral molecule and its mirror images, and we've said that is known as enantiomers. So they are both enantiomers of one another. They are non-superimposable mirror images of each other. Let's look at another example. So is 2-hydroxypropanoic acid chiral? You're going to identify the stereogenic center, draw the molecule as a tetrahedral structure using this template that we're going to get very used to, and then you're going to draw its mirror image or its enantiomer. So I'm going to go back to my page here. I've already forgotten the name of the molecule, so we're going to flip back. 2-hydroxypropanoic acid. 2-hydroxypropanoic acid. So first of all, prop tells me I have prop, 3, not pent. So propanoic acid. So when I have propanoic acid, I'm going to have a carboxylic acid, so O and OH, and again 2-hydroxy. So an OH, and everything else is just hydrogens. Don't be worrying about that one so much, just because we haven't really looked at carboxylic acids and so on, but this is our propanoic acid. So again, label my carbon 1, 2, 3. Do a quick scan of what could possibly be chiral and what could be achiral. We have a carbon here on carbon number 1, and it has 1, 2, 3 hydrogens. That cannot be chiral because it does not have 3 different groups, or 4 different groups, sorry. Carbon number 2, we have a lovely OH group up here. We have a hydrogen. We have a methyl group, and we have this COOH group. So that carbon number 2 most certainly is chiral. Carbon number 3 is a weird one. It's a new one because we have this double bond O that we haven't yet encountered. When you have a carbon double bond O, you treat it as a carbon, and this is only in stereochemistry, you treat it as a carbon with 2 single bond O's. So your C double bond O, OH, and we're just going to say CH3, for example. Let's just make one up here. That's the same in stereochemistry only as saying oxygen, oxygen, our CH3 and our OH stay the same. And if we were looking at that, we'd say, well, it has 2 of the same groups here and here, so therefore it cannot be chiral. Okay, so that's how we treat anything with a double bond or triple bond. So in this molecule, we only have 1 chiral carbon, that is carbon number 2. So now I'm going to crack out my lovely tetrahedral template. I'm going to draw everything based around that. So I have my OH, I have my CH3, I have my hydrogen, and now again summarize this, COOH. That's all you need to do. Once I have that done, draw my imaginary mirror, and now draw its mirror image. What is close on one side is close on the other, what is far on one side is far on the other. Okay, and I've done that backwards, haven't I? So that dashed line was closer, and that other line's going away. So I have OH on top. The furthest thing on this side is that CH3, so it's going to be the furthest thing on this side. What's closest on this side is that COOH, so COOH, and again I'm drawing carbon to carbon bond because that's how it is, isn't it? That's how it exists, it's carbon to carbon. And the last thing is that H. And I've done what I've been asked, okay? So I've drawn out my structure, identified the chiral carbon, drawn the chiral molecule focused solely on that chiral carbon, and I've drawn its mirror image. It's an enantiomer. So that's what you're being asked there. The same can be true for cyclic compounds, okay? So your stereoisomers don't only exist as linear flat structures, okay? So they can exist in big, complicated structures, and they can exist in cyclic compounds. So just be cautious of that. So cyclic compounds can have your chiral center again, and we can do this very, very quickly by saying, does it have a plane of symmetry? So if I folded or drew a line down the center of the molecule and I folded it over, would I find that one side folds over nice and neatly over the other? If it does, it has a plane of symmetry and cannot be chiral. If it doesn't, we may have a chiral molecule there and we have to explore a little bit further. Okay, so maybe we just have a look at the one that's identified as chiral so we can see what we're dealing with there. So 3-methyl cyclopentene. 3-methyl cyclopentene. So cyclopentene telling me I have 5 carbons in a ring. Pentene telling me that I have a double bond somewhere. I'm just going to pop it here. And because I popped it here, and because in the name you haven't been told what number it should be on, we assume it's number 1. So between 1 and 2 I have that double bond, 3, 4 and 5. So the last thing I need is that methyl group on carbon number 3. Now what I can also do to make my life easier is just start popping in those hydrogens where I know they are. Because every carbon must have 4 bonds. And if you're not told what the bonds are, you can usually assume it's hydrogen. Now, I made a boo-boo there because here we have a double bond. So this carbon, for example, already has 2 bonds in that double bond, 3 coming out here, and the last one is a hydrogen, and only 1 hydrogen on each side here because of that. Now we can quickly run through and see which ones might be chiral. So beginning with carbon number 1, it cannot be chiral because again we have that double bond, and remember that's like saying that that carbon, this one here, is bound to 2 other carbons. Okay, so carbon is the same, okay? Carbon double carbon is the same in stereochemistry as carbon being bound to 2 single carbons, and therefore that would not allow us to have 4 different groups. So that one is out. Same rule applies down here. And any of these where we see these 2 hydrogens sticking out, forget about them. So the only one really left is this carbon here. Let's explore that a little bit more. So my lovely blue carbon, I have a hydrogen sticking out, I have a CH3 sticking out, and then draw that line down the middle. Okay, so on one side you're going to have this bond coming out, which is a CH2, CH2. I know that doesn't make sense because we know that should be CH3, but just in this sense, stick with me. And on this side we have a CH, CH, CH. So you can see that there's 4 different groups going on there because this double bond is obviously different to this single bond on that side, so it makes it 2 different entities. Okay, so for that reason, you can say in this structure, the overall molecule is chiral, and your chiral carbon is this one right here. Okay, so just so you know where that's coming from. You can practice these in your own time, and then if you have any questions on them in the lecture, we will absolutely go through them. Now, we've already said that we have a chiral molecule, and you draw its mirror image there, known as enantiomers. And no matter what we try and do, we can't interconvert them. They are 2 standalone atoms, or 2 standalone molecules, okay? They differ in their spatial arrangement of atoms, and there's nothing we can do to change that. Because they are 2 very different molecules, they do have some similarities, but they do have a key difference, okay? So they're similar in they're identical in their melting points, their boiling points, so those kind of physical properties. They're identical in their solubility, and they're going to have the exact same iris spectra. Okay. Whoop. But, and I'm going to come all the way down here, they have all of those same physical properties, except they differ in their interaction with something called plane polarized light. What does that mean? So plane polarized light. When we have light, remember light functions as a wave, okay? And it doesn't just go in one neat line, it takes up many planes, okay? So it takes up many axes. And when it's looking like that, it's called unpolarized light. And we can take advantage of this, okay? And we can use an instrument called a polarimeter, which we will be using in the lab. And we can determine, okay, the interaction between a chiral compound, okay, something maybe like aspartic acid. If you draw the structure out of aspartic acid, you'll see it has a chiral carbon. And because it has that chiral carbon, it can interact with light in a certain way. If I have a solution of aspartic acid and I compare it to a solution of just pure water, we'd see a difference in how they interact with this light. So if I had an achiral molecule, so just water, plain water, I'd take my light, I'd put it through a polarizer, okay, and that just means it takes it from the light being dispersed in all sorts of directions and focuses it in one direction, okay? It plain polarizes the light. I then pass that light through my solution, okay? So we're going to have a long tube with a solution. If your solution is achiral, the light will come out at the exact same angle as it went in, and it's not been rotated. However, if I take a chiral molecule with a chiral carbon, 1 or more of them, I take my light, I plane polarize it, and then I pass it through my sample tube. The interaction between that plane polarized light and your achiral molecule will cause a rotation of that light. It went in completely vertical, okay, maybe at a 90-degree angle, and then when it comes out, it is slightly more rotated. Okay, so we can actually determine how much it has rotated. Okay, so the instrument, the polarimeter, will give you a value. Okay, and this ability to rotate that light is known as optical activity. And your chiral molecules obviously can rotate it in one or the other direction. They can rotate it to the left, and that would give us a minus value. And it could rotate it to the right and give us a positive value. And therefore, if we had one enantiomer that gave us a positive value, or rotated our light to a positive degree, its mirror image would rotate it the other way and give us a negative value. Okay, so that might sound a little bit abstract, but we'll actually be able to do that in the lab and you'll see what goes on. And we use this calculation, okay, so calculating specific rotation. And this formula, I do ask that you learn it well, okay? You do need to know this formula off by heart, and it's a common enough question to come up on an exam paper, and it's also one of your worksheet questions. Okay, calculating the specific rotation. So what does this mean? Because it's just a random bunch of letters, isn't it? So alpha D. Alpha D is specific rotation. And you are always going to be asked, in this module anyway, to calculate the specific rotation. So you, for all intents and purposes, can call this X or unknown. Alpha observed is the observed rotation. That will be provided to you in the question, or in the case of the lab, you will get that value from the instrument. Okay, so it's the rotation of the light in degrees, and it'll either be a positive value or a minus value. Next we have on the bottom is L times X. L is for length, it's the path length of your polarimeter tube. So again, in the lab you will measure that yourself, and you'll measure in centimetres because that's where your ruler is going to be in. But in this formula, you need it in decimeters. So to go from decimeters to centimetres, you must divide by 10. Okay, so sorry, to go from centimetres to decimeters, divide by 10. You always want your number in decimeters. The last thing is concentration. Your concentration units must always be grams per centimetre cubed. So you must know those three things, very, very important. Let's look at a little calculation. So let's do a practice question. So we have an aqueous solution containing 1 gram of sucrose in 100 ml of water. And I wonder if I can draw on this. And I can. Wonderful technology. Okay, so I have 1 gram in 100 ml of water. I have it in a 2 decimeter tube, and I get the observed rotation of plus 133. I know that my specific rotation, so my alpha D, is equal to my observed rotation divided by my concentration times my length. I know my concentration must be in grams per mil. Do I have grams? Yep. Do I have mils? Absolutely. So I need to get that in. I'll go from 1 gram per 100 mil to just how many grams in 1 mil. So all I do here is just divide by 100, isn't it? So I am going to go and do that very quickly. So that's going to be 0.001 gram per mil. So that's my concentration that's dealt with. The length of my tube, L. Here in this question it's been given to me in decimeter, so I can keep it exactly as is, 2 dm. And they've told me what my alpha obs is, my alpha observed, is plus 1.33, and the units here are degrees, okay, because it's a rotation, it's an angle. Once I have all that information, I can sub it in. So alpha D is equal to plus 1.33 degrees divided by a concentration of 0.001 times 2. That'll give me, I'm going to keep that plus value the whole time with me, okay? 0.002, and that would give me an answer of plus 66.5 degrees, okay, because it still is a rotation. Okay, so this is my answer. So the calculation isn't tough. I think most students usually find them fairly okay, so it's just a bit of practice. The main area you can go wrong is this, just forgetting the actual value, or the actual equation. Let's look at one more. We have an aqueous solution containing 4 grams of aspartic acid in 50 ml. The observed rotation is measured in a 20 centimeter sample tube and gives us an observed rotation of minus 0.566. So I should always be provided with those 3 pieces of information. If I don't have the 3, I can't do the calculation. So again, I know alpha D is equal to alpha observed, my observed rotation, divided by concentration times length. Concentration. I have 4 grams in 50 ml. I need that in grams per mil. So I divide it by 50. So that is going to give me an answer of 0.008 grams per mil. My length here is in 20 centimeters. I need to get to decimeters, so I divide by 10. So that's a conversion you just kind of need to know. Centimeters to decimeters is always divide by 10. Okay, now I have, and I know already, sorry, my alpha observed, we were told, is minus 5.66. Okay, and again, make sure you keep that minus value with you because it is important. It's specific to the enantiomer. So alpha D is equal to minus 5.66 divided by 0.008 times 2. It's the same as, I'm just going to keep my degrees up here, 5.66 divided by 0.016, which will give me a final answer of minus 37.38 degrees. Okay, so this is my answer here. Okay, so 2 main things that you need to leave this video feeling a little bit, maybe not 100% confident, but a little bit sure of. Your specific rotation calculations, can you do them? Okay, you can use this video to help you do the calculation in worksheet number 2. And then, can you identify a chiral carbon? And could you draw out that tetrahedral template based on that chiral carbon? And finally, could you draw out its mirror image, its enantiomer? Okay, I think you should be fairly okay with those. The main thing that does often catch students out is, where are we? Is summarising these groups, okay? But we'll draw our attention to that, we'll work on that as we go forward, and particularly in our stereochemistry labs. So, I'm going to leave that here, and again, if you do have any questions after this video, please feel free to let me know either by email or in the following lecture. Thank you very much, guys. Chat soon.